Good morning. Good morning. Kuya, mura naman lagi gabi sa inyo ha. Anyway, it's depend naman on what part of the day kaning tanaw is either morning, afternoon or evening. For this reporting and for the sake of formality, I will use morning. So again, good morning. I'm Lemuel John El Taghoy, or you can call me Kuya. Today, I'm going to attempt explaining a certain topic, which is a special relativity theory. Special relativity theory. Kuya, di ba physics mo na? Mm, physics yun siya. Magdugo ito atong ilang anong subject ka. Listed siya. So, allow me to explain this topic by using a vernacular language due to the reason that by using it, I can deliver this reporting more freely, and also you as a watcher or a learner can easily understand. So, now let's proceed. By the way, along the way, while I'm reporting, maybe you can observe na dili kay nako ginabasa tanan. Don't you worry, ginatoy na nako due to the reason na there are some information na I want to impart sa inyo na wala dira. And also there are mga pages na dili kay nako gina-focus because like understandable lang siya. And also, if kung paminaw ninyo wala mo kaapas or ganahan ninyo mas masabtan, you can pause the video and take time to read kung unsay naa sa screen. Okay, padayon ta. Special relativity theory. Again, murag natay problema, murag may ugly face kinakapod sa. Okay, let's try to solve this one. For now, tayog na sa baas mga bakya eh. Ay, taning kadlawon mag-record. Anyway, so much for that. Okay, parenta. Objective of the reporting. State and discuss Einstein's two postulate regarding special relativity. 1. Demonstrate your understanding of time dilation and apply it to physical problems. Demonstrate and apply equations for relativistic length, momentum, mass, and energy. Special relativity. Einstein's special theory of relativity, published in 1905, was based on two postulates. 1. The first law of physics are the same for all frames of reference moving at a constant velocity with respect of each other. Second, a free space velocity of light c is constant to all observers, dependent on their state of motion. Muna siya ang value sa speed of light. 3 times 10 to the power of 8 meter per second. Rest and motion. What do we mean? What do we mean when we say that an object is at rest or in motion? Is anything at rest? Na picture dira. Unsay makita nimo, maybe you will say na ay tao naglingkod, na ay lamisa, na ay telephone, na ay computer, then why naglihok? May naglihok ana. You sometimes say is that a man, computer, phone, and desk are at rest. Sakto man sad, pero we forget that Earth is also in motion. Like Earth itself is moving. What we really mean is that all are moving with the same velocity. We can only detect motion in a certain or in reference or something else. Like, let's try to discuss it further in the next page. Frame of reference, considering the velocities of 3 different frame of reference. So, okay. Ups. Let's back. No. Okay, and it as a first picture. Earth as a reference, a bicycle or ang nagbike kay nagdagan siya to S with 25 meter per second, and also the platform kay nagdagan siya to S and 10 meter per second. Considering that the Earth itself is moving, then if there is a man observing or naitawo nga nagtan-aw nga nagbarog lang sa yuta, makita niya nga wala lang naglihok, like wala naglihok sa imabaw, it's constant. Tapos anita sa second picture. Okay, ani nga picture kay ang tao or ang nagbahay kay nagdagan 35 meter per second and a platform kay wala siya nagdagan. Then if you are a man, an observer nga nagbarog lang, then you can see that nagdagan ang or there is motion equivalent to 10 meter per second. And third picture ang bicycle kay wala nagdagan and butang natog ang reference or ang platform kay nagdagan siya 35 meter per second to the east, and you as an observer nakita nimo nga naglihok ang platform nga naay bike 25 meter per second. Let's try to understand it as we continue this reporting. No. Okay. Constant velocity of light. Siguro, musugot man kay sa dili, speed of light is always speed of light. No matter what the situation, ang kakusugan sa speed of light is same constant. Like, the value of light is 3 times 10 to the power of 8 meter per second. Bisan asap man kang perspective whether naamang ka sa earth or nasa speed. Nasa space. Now, unsa man din ang stimulus event? Just imagine nga naay isa ka tao nga nagtungtong siya sa train. Tapos naa say usa ka tao nga nag-observe. Ang tao nga nagtungtong sa train, butang na to isa ka bai, she sees nga naay light, but ang light kay kanang permanent lang bitaw nga nagsiga, or like nagsiga lang siya in naa sa iyang permanent place, is in sa position nga asa siya nagsiga. But lahi nga scenario ang nakita sa isa ka tao nga nagbarog dira sa gawas. Like iyang nakita na ang light nagdagan continuously or gikan sa kinahanglan sa last sumpay lang tanan. For example, kamantay ka, nakasulay kay kadlawong dako or gabi tapos naay nakars kasada tas naay tao nga nagpakusog igdagan. Di ba makita nimo nga murag ning badlis lang ang suga. Same scenario ani nga event. Time measurement. Since our movement of time involve judgment about simultaneous event, we can see that time may also be affected by relative motion of observer. In fact, Einstein's theory shows that observers in relative motion will judge time different. Furthermore, it is correct. So this is the equations of time dilation. Okay. I think it's self-explanatory. Let's move to the next slide. Now, let's try to apply the formula of time dilation in a certain problem. Ship A passes ship B with a relative velocity of 0.8c, 8% of the velocity of light. A woman aboard ship B takes 4 seconds to walk the length of her ship. What time is recorded by the man in a ship A? So, just substitute a given value to the formula, and we can get 6.67 seconds is a proper time. Now, maybe nakadungog na mo aning twin paradox, but it's a scenario where ang isa ka kaluha kay kana stay in Earth or naara sa kalibutan, walang usa kay naga-travel outside the space. And it happened na pag uli sa naga-travel after 10 years, mas magulang siya og 23 years kaysa nabilin. And the traveling twins' motion was not uniform. Acceleration and force were needed to go to and return from space. The traveler aged more and not the one who stays home. This is not a fiction lang, but it is proven and like real ni siyang hitabuan. Anyway, you can search it more in the internet if na-interest ka aning twin paradox. Now, let's talk about land constructions. Like, dili lang di ay ang time maoy naapektuhan, but also length. Like, since time is affected by relative motion, length is also be different. And mo ni siya ang formula. Okay. Let's try to apply the formula in a certain problem na pod. A meter stick moves at 0.9 c relatives to an observer. What is the relative length as seen by an observer? So, substitute the given to the formula and we can get that the length recorded by the observer is 43.6 cm. Okay. Now, attach a relativistic mass. If momentum is to be considered, the relativistic mass m must be consistent with the following equation. So, this is the equation of the relative mass. And let's try to remember it because magamit ni siya into some problems na pod. Let's apply it. The rest mass of an electron is 9.1 times 10 minus 31 kilogram, which is the relativistic mass of its velocity is 0.8 c. So, again, just apply the given value to the formula and we can get that the mass has increased by 67%. Now, okay, I think masabtan ra ni siya. Like, it's just giyon sa pagkan-up ang formula. And padayon ta. Mass and energy. The conversation factors between mass and energy ay EO equals O C squared. The zero subscripts refer to the proper or rest values. Okay. According to Einstein's theory, the total energy E of the particles is given by Now, let's apply kung sa itong nakatunan giniha from the previous slides to the certain problem. What is the kinetic energy of a proton with a mass of 1.67 times 10 minus 23 kilogram traveling at 0.8 c? Still, using the formula m equals mo over square root of 1 minus v squared minus c. So, just substitute the given and we can get the relativistic kinetic energy key as 0.2 key as 6.02 times 10 minus 11 joules. Now, summary. Muna siya. Einstein's special theory of relativity published in 1905 was based on to postulate. Tapos, muna siya ang mga given formula for the relativistic time, for the relativistic length, relativistic mass, and also relativistic momentum, total energy, and kinetic energy. Okay, that's the end of the reporting. Siguro, wala kayo niyo nasabtan because I understand because lisod yun siya na topic. Wait. Let me show my face. Okay. Ano akong ugly face na pod. By the way, it's 11:09 in the morning. Nagduka na yung tawa. Mm-hmm. Oh, i is a conclusion. I will give a video na kanang it will explain more about this topic about special relativistic theory by Einstein. Hopefully na po may makuha ato. Let me go to that video. Okay? Let me
Professor Dave again. Let's talk about length contraction. He knows a lot about the science stuff. Professor Dave explains. Einstein's special relativity was a huge step in physics. And even though time dilation seems like the weirdest thing you've ever heard, there's plenty more to get through with this theory. As it happens, it's not just time that's relative, it's length as well. And as we will find out, the math tells us that when you approach the speed of light, your measurement of space changes just like time. This is because if an observer on Earth and an observer in a fast spaceship register different spans of time for an event, they must also be recording different distances, since both observers agree on the same relative velocity between them. Specifically, the faster you go, the smaller objects seem to be, and the shorter the distance you perceive yourself to be traveling. This is a phenomenon called length contraction. Here we can see two versions of a spaceship traveling very fast to a faraway celestial object. In one, we see things from the perspective of an observer on Earth, and in the other, we see things from the perspective of someone on board the spaceship. The Earthbound observer sees the spaceship moving at some velocity v, notices time moving at the familiar rate, and can measure some distance for the journey, which we label as L0 and refer to as the proper length, as this is the length that is measured by an observer that is at rest with respect to the objects demarcating the distance. But on the spaceship, the only thing that is the same is the relative velocity v, though in this case it represents the velocity of Earth and the destination as they move relative to the ship. And because this velocity must be the same as for the Earthbound observer, everything else must be different. Because of time dilation, the time interval will be different, delta t0 rather than delta t, and we label the contracted length of the journey as L. The relationship between L0 and L is given by this equation, which can be derived from the time dilation equation. Not only do the two observers arrive at different values for the length of the journey, they even arrive at different values for the length of the spaceship, as this dimension is parallel to the direction of travel. The Earthbound observer would see the ship as being much shorter than the astronaut does. In fact, this discrepancy in length neatly explains how the two observers could perceive different rates for the passage of time. It also explains how fast-moving particles can defy certain expectations, because at such speeds, time slows down, and the distance traveled contracts. So, a particle like a muon, with a half-life of a millionth of a second at rest, is able to exist for longer and travel further than expected when moving near the speed of light, due to relativistic effects. At this point, let's take a moment to make sure we understand how to assign delta t and L values. Delta t0 is the proper time interval, which is the time interval as measured by the inertial reference frame where the two events occur in the same location. For a space journey, that's the spaceship, because the Earth leaves and the destination arrives while the ship goes nowhere. Everyone else, like someone on Earth, will register a longer time interval, delta t, for this journey. L0, the proper length, however, is length as measured by an observer that is at rest with respect to the objects in question, like the Earth-bound observer is in this case. Anyone in motion with respect to the objects, like the person on the spaceship, will register some shorter length for this distance, L. This means that the proper time and length may not always be measured by the same observer, and we need to know how to assign these in order to do the math correctly. Let's say a ship is traveling from Earth to another system at 90% light speed. The person on board measures the journey as being 8.2 light years in length. How far away is the destination according to someone on Earth? Well, we can plug in 8.2 for L and 0.9 c for V. Then we just do some algebra and we should get 18.8 for L0, or the proper length between Earth and the destination. We still have more to go with special relativity, but first, let's check comprehension.
Okay. Um, Hopefully somehow na amoy nakatunan for this reporting, and I admit na even ako mismo dili pa win ana ka broad akong dili pa win ana ako nakatunan ani nga topic because it's very broad, but still ano lang, let's try to research more, learn more, and anyway, um I will end this reporting, and thank you for listening, and God bless.